Good day, everybody. This is Dr. Gopal, and I am presenting my talk on metrology-characterization of precision optics for laser applications. My background is applied optics, and during the course of my work, I strayed into precision mechanical machining, etc. So this talk is primarily about the metrology, that's the main measurement of optical surfaces and optics as used in with the laser applications. So without wasting much time, let's go forward. What is metrology? Everybody knows that metrology is nothing but a study of measurements. And why measurements? Measurements will tell you whether you got the component as per the design sheet or not. And there are specifications which you have to meet. Okay. Measurements are in two ways. They are qualitative as well as quantitative observations of the operator. And they serve many purposes, one of them being the legal purposes as well. Generally, what happens is when somebody takes a component and the report sees that everybody thinks that the measurements are good. What do you mean by good? Good measurement, there are few characteristics of good measurement. Good measurement is a precise science that measures physical quantities within very tight tolerances, the given tolerance as per the design sheet, and thereby minimizing your uncertainty or randomness. We all need, any system developer, any scientist needs a good measurement of all the parameters of a given system, particularly any system, and particularly when we are talking about precision optics, it is all the more necessary. So how to get good measurement? When we are talking of good measurement, first and foremost is the operator should be aware of the equipment which he is using for measuring a given parameter and its appropriate use as well as its optimal use, how to get the best out of the equipment. Then he or she has to prepare a proper protocol for measurement of a component for a given set of parameters on that equipment or the series of equipments in order to reduce or avoid randomness. This will also help in minimizing your uncertainty. And then comes another very important thing, the equipment which is being used, that should be properly calibrated periodically and should be well maintained under the advice of the vendor who has supplied the equipment to you. Now, and this good measurement, this will also give you other advantages, like it has accuracy and interchangeability, repeatability, and your quality is assured, and your manufacturing process will have some flexibility, which again helps in optimizing your production cycles, and thereby the timely deliverance will be high, and then the machine down times will be low, and then most importantly in the R&D domain as well as in production domains, the production also and the R&D domain also, the determinism means zero randomness or minimized randomness, and precision will also be incorporated. So this again helps in a set of customized metrology requirements also. There is always a discussion about what is accuracy and what is precision. Here it's a very simple example that you are going through. Precision is consistently giving a series of measurement, whereas accuracy is reaching the target. You can see two examples. In the example on your left side, you see high precision, means all the 4 points are there very close. However, they are pretty far from your target. Whereas on the right side, you see the accuracy is good. It is within the innermost circle. However, they are not pretty close. So it is called a low precision and high accuracy. Anyway, this is just a passing thought. We'll go further. Let's talk about the parameters of interest in optics, particularly laser optics. When we are talking of parameters of interest, what are these parameters? Are they physical parameters? Are they mechanical parameters? Or are they some other things? You can see physical parameters include refractive index, thickness, absorption coefficient, transmission, reflection, turbidity, the material features, and then some geometrical dimensions like length, angle, thickness, surface, and etc. And then one point I did not talk about is surface quality. When we say surface quality, how do we measure that? So this surface quality is something which is very dear to all optics developing people as well as the users. We'll talk about it. In fact, this talk is dedicated to optical surface quality only. Now let us just take a little aside from metrology to what is aspheric. What is an aspheric? We all know that all optical systems use plane surfaces, spherical surfaces, as per the system requirements, specifications, as the facilities available and the funds available. However, there are systems where aspherics, when I say aspheric, non-spherical surfaces are also being used. Most of the optical systems, about 95 to 98 types of 98% of the optical surface systems use only spherical surfaces with a given radius of curvature. However, these surfaces, spherical surface, will meet your requirements only up to a low level as well as a medium level. But when somebody is looking at ultra high precision systems and cutting edge measurement, cutting edge performance, near theoretical performance in advanced optical systems, where your performance is as good as should be as good as theoretical limit in terms of resolution, intensity on the image plane, spherical surfaces do not deliver the desired performance. Added to this, there is another issue called, there are other issues like footprint, how much the system is occupying, what is its volume, the bulkiness, and its weight. These three things become very important when you are talking of compact systems or space systems or astronomical systems. Even in normal laser optical systems also, these three parameters are very important, that is footprint, volume, and weight. So there one has to go for non-spherical surface, that is aspheric based optical systems. What is an aspheric system? Let us see. What is aspheric? Any rotationally symmetric surface with its optical axis which is not spherical, where the radius of curvature is not constant throughout the aperture, is called aspheric surface. There is a simple equation: Z is equal to CH square divided by 1 plus 1 minus 1 plus K, C square H square plus higher order terms, where C happens to be the radius of curvature of the base radius of curvature. As I mentioned, the radius of curvature of an aspheric surface changes from the center to the aperture constantly, whereas in a spherical surface it does not change. Whatever is there at any point throughout its aperture, the radius of curvature is same. Whereas in an aspheric surface, the radius of curvature at every point progressively changes from the center to the edge or edge to center, whichever you are looking at. Now C is this radius of curvature, H happens to be the aperture at where you are looking at, and Z happens to be the sag or the height or depth of the surface from the median, and H is your semi-aperture, as I mentioned. Then these A1, A2, A3, A20 are all your aspheric coefficients, and K happens to be the conic constant. The conic constant varies for different types of aspheric surfaces. It is 0 for a sphere, -1 for a parabolic, and less than -1 for hyperbolic, and it is higher than 0 for an oblate ellipsoid, or in between -1 and 0 for a prolate ellipsoid. So primarily there are 4 types of aspherics: parabolic, hyperbolic, elliptical. And the fifth one is a very special case, spherical, where K happens to be 0. Now, the best part with this is, in metrology of an aspheric, is the same equation, what you are looking at here, is used for designing of the system, and then fabrication of the system, as well as for the measurement of the system also. So this is the best part. Now let us see how it goes further. Oh, by the way, why should one look at aspheric only? What are the advantages? If you just go through the fundamentals of optics, optical systems suffer with monochromatic aberrations and chromatic aberrations. Monochromatic aberrations are caused because of the differential refractive indices of the different materials that are being used in an optical system. Because one material and another material, they focus at different points as per the spectral lights. E line, G line. E line means, for example, G line corresponds to green, and D line corresponds to yellow. When you go from one spectral line to another spectral range, the focus points will continuously change. So, that is called our chromatic aberration. Even when you use single color also, one spectral length also, there also, depending on the curvature of the surface, spherical aberration, coma, astigmatism, field curvature, or distortion, these 5 aberrations will be there. Aberrations are defects, you can say. Because of these 5 defects, the intensity of the light coming from the object plane onto the image plane is severely affected. So this will render low intensity on your image plane, so which is not desirable. This is because of the Snell's law. And what happens is because of this, all these five defects I mentioned: spherical aberration, coma, astigmatism, field curvature, and distortion, these aberrations will play a major role, and your desired intensity on the image will be very less. So the task before the lens designer as well as the optical fabricator and the optical system user is how to avoid, you cannot avoid by the way, how to reduce these defects. So that is where we use lenses with higher power, so that the higher power would reduce my spherical aberration, or lenses with minimum spherical aberration. These are two different things, but they will not give you perfect solution. So another better solution is use a material with higher refractive index, so that, and also split these higher power lenses into two lenses or three lenses or more lenses. That is also one solution, whereby what is the advantage is your spherical aberration is reduced, your coma and astigmatism, etc. are reduced. However, number of lenses would increase in the system, which will render the system bulky, heavy, and difficult to manage and manipulate. So when these two methods are failing, higher power lenses as well as higher refractive index lenses, they are not working to the advantage of the user. Another option is simpler, as well as the best option is to aspherize the surface. You select out of the whole branch of the lens surfaces of the system. You have to optimize which one would give you aspherization of which surface would give you a better surface quality, better intensity on your image plane. This one has to, it comes out of practice, it comes out of iterative design process by the designer. So aspherization provides improved performance, while your total system length as well as weight and footprint are also maintained within limits. So these are the benefits. Aspherics minimize aberrations, it will reduce the number of lenses in a system, and the weight is also reduced. And when you are developing systems with in bulk, thousands of systems we are talking about, then in each system, instead of having 5-6 components, if you can get the job done within 3 components or 2 components, the total cost also comes down. And there are systems where exotic designs can be used to develop multiple application domains. So aspheric, the benefits of aspheric many a times overshadow the disadvantages of the inherent disadvantages. We'll come to that a little later also. What are the application domains of aspheric applications? Laser optics, as I mentioned. All your compact disc objectives, whether it is audio systems or video systems, and then lithographic objectives, particularly for very large integrated systems, and IR optics, all IR optics, security scanners, head-up display, and helmet-mounted display for your aerospace applications, night vision systems, augmented reality and virtual reality systems, and pilot training, terrestrial, all telescopic systems. Consumer optics, when I say consumer optics, I'm talking about, let's say, the day-to-day consumer product that we are using, a mobile phone, for example. The mobile phone has a very small lens, which is primarily an aspheric surface, hardly 4 mm diameter and maybe 6 grams. And zoom systems and photographic systems, X-ray systems, all progressive lenses are primarily aspheric surfaces. And there are many low vision aids and biomedical optics also where aspherics has to be used. Now, how to make an aspheric? How to develop an aspheric? Design is one aspect. Development of an aspheric surface itself is a big subject. I'll not get into the details of that. Simply, it is enough sufficient to say that instead of following the traditional grinding polishing, we will go to the turning of the component. Turning, when I say turning, means using a mechanical engineering machining method, whether you turn the component or mill the component. So there are many methods. Now the question is, how can we turn glass? The answer is a no, to a large extent. There are, of course, turnable glasses are also there, but mostly I'm talking of turnable materials which can be used in a multitude of applications by developing aspheric surfaces, aspheric profiles. Now, when I talk about turning of a surface for optical applications, what is the difference between a normal machining? We are talking of a turning in a lathe machine in a normal mechanical workshop, and a ultra high precision turning required for optics. The difference is in terms of the precision of turning as well as the surface quality. So I will not get into those details. Sufficient to say when we talk about metrology, then these things will come into play. Okay. Now let us talk about exclusively only for metrology in this presentation. Maybe some other time we will talk about fabrication also. Let us assume that the surface is developed by turning method. Now, this turning method which I am going to talk about is developed by using diamond turning method. We have developed a surface, an aspheric surface. Now, how do we characterize or how do we measure the surface to ensure that it is meeting all the desired surface specifications in terms of its geometrical dimensions as well as the surface characteristics. Now I am using two different terms. One is metrology, another one is characterization. When I say metrology I'm talking of dimensional metrology. What is its diameter? What is its radius of curvature at the center? What is its thickness, etc.? These are called dimensional metrology. And I'm talking of characterization. Characterization means whether the surface, the radius of curvature is as per at a given point, is as per the design sheet. If not, how do I measure it? How do I check it? So for that's where my contact method and sometimes non-contact methods also come. We'll talk in detail about that in the coming slides. There are different methods. For contact, we use 3D coordinate measuring machine, and contact profilometer we use. We are actually we are profiling the whole surface by using a stylus, that is called profilometry. And then there are non-contact methods. We don't touch the surface with any stylus. However, we use a laser beam for that. So confocal microscopy, and then we have interferometry also. There are other methods also. We'll go through one by one. Now, as I mentioned in the beginning, there are two methods of optical fabrication. One is by traditional grinding polishing, another one is by diamond turning. When I talking about grinding polishing, the surface is primarily a spherical surface. When I say spherical surface, the light that is incident on the surface would give you a spherical wavefront, which in interference with the test surface, in a target surface, will give you will cause, due to interference, will give you some fringes. So profile accuracy or inaccuracy or lack of accuracy will be characterized by using interference with test plates as well as Newton fringes, etc. This is for grinding and polishing normal spherical surfaces. And how to measure the roughness or the finish of the surface? There is something called scratch and dig, which is a simple method. However, it is a traditional method. Now, how about non-spherical surfaces? There, these methods will not work because the interference patterns for a spherical surface is very simple to understand, analyze, and to interpret. Whereas in case of aspheric surface, the situation is very different. We'll show you some figures later. So there, instead of using interference or non-contact method, we go for contact method by using a contact profilometer. There, the error of the profile is measured in terms of the departure from the surface, departure from the desired surface in terms of the resultant sag or sagitta, or the depth or height of the surface. The desired height and the actual height, the difference between these two is the error. So the change between the error that is produced during the fabrication is measured in terms of the sag error, and that sag error will be reinterpreted as the departure from the desired profile. So that is one part. And second part is finish or roughness. Whether the roughness is within the tolerances or not, that is another story. So a typical equation of why, by the way, roughness comes in a spherical non-spherical surfaces. You are continuously turning the surface, so the tool marks will be there on the surface, and the tool marks will cause some periodic grooves, and the periodic grooves will cause this roughness. The equation is given as PV, the height of the periodic surface, F is the feed rate of the tool on the job, and radius, the tool which is doing this, the radius of the R is also covered, tool is also coming. So this is all. Now let's come back to interference. What is and how is interference? What is interference? When two sources of intensity, light intensity or photonic intensity, are interfacing with each other, are interfering with each other, then what you have is something called an interference. You can see a simple figure. And what is an interferometer? Interferometer is that device which creates interference between beams of light coming from a test sample as well as a standard sample, and then analyzes that. that interference. But of course, this interference has to be created under controlled conditions so that it will be easy for the operator or easy for the scientist to analyze, study this, observe this, analyze this, and interpret it. Knowledge of the conditions under which the interference is created, this knowledge would allow us to draw conclusions about the error in the surface. In fact, you are really studying or observing the interference patterns on the surface between a test sample as well as a standard sample. So those fringes are manifestation of the error of the prepared surface. So this is the schematic. And then there are, just for the sake of understanding, interferograms. There are two types of interferograms. One is a constructive interference, where the amplitudes are geometrically added to each other. You can see this on the right side of this. Here you can see the amplitude is doubled, and there is something called destructive interference, when the amplitude of two beams annul each other, and what you have a zero intensity, which is called destructive interference. And you have this series of constructive, destructive, constructive, destructive, etc. continuously. So this will give you white and black bands. Then a plane surface, if you see the figure here, your top left, a plane surface will cause this, a spherical surface will cause this, again a dark and bright, and on the step surface, and an irregular surface. This is of interest to us. When I say an irregular surface, we are talking about a spherical surface with some errors, or a non-spherical surface with a bunch of errors. This is what we are talking. Now, each fringe pattern, it contains the full information of the surface. In other words, the character of the surface which has been developed is within the fringes. Now, when I say characterization of an optical surface, I mean this. You are looking at the character of the surface rather than measuring its length, width, or thickness, etc. It is something less. When you talk a person, okay, there are physical attributes, how tall he is, what is his color, what is the color of his eyes, etc. This is dimensional metrology. When you talk about, okay, he's a good person, well-behaved person, etc. No, all these things are character of the thing. So optical surface has two sets of different features. One set is its geometrical dimensions, another one is its surface characteristics. In case of spherical surface as well as an aspheric surface, the characteristics of the surface characteristics are of interest to us, and interferogram are the tool which all people are using to analyze the surface and to interpret the errors that have been caused during the fabrication or maybe assembly. So these are of interest to us. A typical phase shifting interferometry is shown here. It's again, of course, non-contact. Here the capabilities are, it depends on the system that you have chosen. It can be good for MTF measurement, modulation transfer function, or point spread function. And finally, you are looking at the encircled energy at the image plane vis-a-vis the energy that is coming into the system. Okay, now let's talk about aspheric testing. When I say aspheric testing, there are three major parameters. When I talk about the surface characterization, we are not talking about the geometrical dimensional metrology. We are talking about the surface characterization of the aspheric surface that has been generated. So here we see that there are three major parameters. One is called form, second one is called figure, and third one is finish. For mechanical engineers, the form and figure is called waviness. The meaning is how much is departure from the desired profile. A very broad way of talking about it. And the third one, finish, is what is the roughness or what is the smoothness of the surface. Whereas for optics people, that waviness has two connotations. One is form, another one is figure. I'll come to that a little later. To measure these three, there are, as I mentioned in the previous slides, contact methods and non-contact methods. For contact, you need a jaw-specific and profilometer, which with the desired surface quality, with the desired accuracy. And then the stylus that you select to scan the surface, to profile the contour of the job workpiece, the stylus has to be suitably selected. And then what is its diameter, what is its size, how far it can move, and what is its mobility speed and its direction. All these factors will affect your metrology, your characterization process. And for rough and fine machining, you use ruby styli just to measure the form and figure. And for ultra fine machining, you go for diamond styling or sapphire styling. That will tell you both your figure as well as finish. There is a non-contact method also, but that comes only after the individual surfaces are well, properly fabricated and ascertained. That is important. Now, let us see what is the difference between form, figure, and finish. We'll come to that within a minute. These are typical parameters of the stylus that you use. All right. What is form? What is figure? Form is form error when you say, let us say you want a spherical surface, just for the sake of argument. You got an aspheric surface, or you wanted a elliptical surface with the base radius, let's say 40 mm. Instead of 40 mm, the base radius is, let's say, 42 mm. That is called a form error. Why this error comes into play? The reasons, the broad reasons, there are four. Let me go from the bottom one. Worn out tool. The tool has worn out because of excessive use. So the radius of the tool, the diamond tool, has slightly changed. So in other words, the center of the tool, which is supposed to remove the material from the workpiece, is not removing the way that it should at the desired point. So the worn out tool is the major contributor, and your workpiece is not properly stress released before the machining. Third one, of course, thermal effects are also coming into play. This is itself a big subject. We'll not get into that. How you are holding the workpiece on the machine. If you hold it tightly, then after the machining is over, there is a spring back effect. If you hold it loosely, then there is slight movement of the job or workpiece, and the tool will not work properly. So these five reasons are the main cause of change of radius of curvature of the aspheric surface at the base as well as progressively throughout its aperture. So this cannot be accepted. This has to be avoided at all costs in the beginning stage. Once this is taken care of, then comes your figure error. Figure error is nothing but, okay, you meet the radius of curvature broadly, but there is still some error. That some error is in terms of wavelengths, optical wavelengths in which the optical system is designed. Let's say for measurement purposes, broadly 0.6328 microns is the baseline optical wavelength at which all the optical surfaces are characterized. So 0.6328 or 633 nanometers, whichever you consider. This is the template based on which the surface waviness or a figure is mentioned. Let's say this is called as the lambda or one wavelength. It should be less than a wavelength, less than half a wavelength, less than quarter of a wavelength. This criteria is decided by the designer. So the job of the fabricator is to make sure that the surface is made within these restrictions, and the job of the metrology people or the surface characterization team is to ensure that what is fabricated and to measure it and to characterize the surface and to tell the user whether it is within the desired tolerances, error tolerances or not. So that is where the waviness comes into play. And the third one is roughness. Because of the vibration of the tool on the job due to many external factors and internal factors, there is a zigzag pattern. There is a peaks and valleys at a very localized domain on the surface from the RMS mean line of the desired radius of curvature profile. So that is the root cause of roughness. Now, these three parameters of characterization are very important for an optical surface characterizing team. So this is how, again, same thing I explained in a different way, but this is it. So as I said, form error is primarily radius of curvature error. Figure error, it is seen in terms of peak to valley as well as RMS or any other measures also. Roughness is an arithmetic average. Most of the mechanical engineering people as well as optical engineering people, they are happy with looking at the arithmetic average, that is called RA or RQ. And the best method is going for power spectral density. That's a bit advanced method. We will not discuss that here. But anyway, that is a Fourier transform of the total roughnesses or total peak to valley departures of over a given sample length. So that is power spectral density. That gives exactly the roughness of the or smoothness of the surface. So that depending on the application that you are having, this roughness, this which method is to use, whether RE is sufficient or RQ is sufficient, or one has to go for power spectral density PSD, that decision can be made depending on the application domain. So these three parameters. Okay, I think we already covered this, so let me not spend more time. So what is the simple principle? The principle is very simple. The working principle is pretty simple. You have a surface and you put your stylus on that with a transducer behind it, and the undulations of the surface, the stylus goes over the undulations of the surface and it goes over from center to edge or edge to center all over the surface, and these vibrations, the stylus vibrations, are transformed into through a transducer in terms of the surface sag. Rather, sag means has it heights and lows, depths, of course, and this will be, and then coupled with the software, it can analyze the whole thing. So this is the typical working principle. And however, still spheres are being used in many optical systems. Why one should not adopt completely aspheric systems, completely aspheric surfaces in an optical system? One cannot do that for two big reasons. One is spheres are easy to make. Whereas aspherics need a lot of pre-preparation during the grinding, during the fabrication, as well as during the metrology. And also it needs highly skilled manpower for both the purposes, and also a very experienced and wise designer to design one. So in order to cut down the cost of the overall production, still even now also spherical surfaces are being used. But of course, whenever it is mandatory because of the desired performance criteria, spheres are also being used. I talked about this form, figure, finish. These are the specifications for a given profilometer. Depending on the brand, the make, as well as the model, your specifications of the profilometer will vary. Now, after every operation, after measurement of a given component set of number of components, the stylus, the profilometer needs to be calibrated. For that, you need to have a standard template, and there is a protocol also. So this is for the ultra high precision characterization, and for a broad characteristics, you don't need to worry about roughness there. Only form and figure are needed. You can go for a three-dimensional coordinate measuring machine. So I think I gave it once again. Figure error may arise because of vibrations, work deflections, chatter, or strain in the material and tool surface non-uniformity, or tool and workpiece non-uniform interface also. So finish, as I mentioned, due to the regularities of production process, material composition, also the heat treatment. Form error is, as I mentioned, by part being not firmly hold or extra hardly hold, or the cutting tool is not calibrated. So why do we need to have a good surface finish? The reason why do we do all this study? First of all, we have to control the process. We have to monitor the process, as well as there are parameters which can be controlled. There are some that cannot be controlled. If you cannot control, then monitor them so that you can predict. One is so that you can predict the behavior of the component, and also you can monitor the component performance. So these 3 points: process, control, or monitoring, can help you in predicting the component's behavior in terms of its surface quality and dimensional metrology, which will help you to monitor and predict the component's performance when it is assembled in a larger system. So what you don't want on a surface: deep valleys, peaks and valleys. Deep valleys or high peaks are not needed, because they will cause, or they will originate cracks propagation. Too many peaks, surface breakdown will be there, wear will be very high. Excessive waviness may cause noise or indicate machining problem. So we have to remove that. I just to show how form error comes into play. Tool path definition, and then this is the radius of the tool has changed. So you can see here on the top left, the contact point should be the bottom one, whereas in reality it is not that. So this will cause either by the wear of the tool or by improper positioning of the tool. We never know what is the cause. But also, instead of going to the center of the workpiece, if the tool is slightly positioned above, a little bit above or below, or an X direction also, not only in Y direction, but X direction also, we call that an X offset. When that tool is slightly offset in X direction, you have an M shape or a W shape surfaces, errors on your surface. We call that an ogive error, which is again not desirable. So how to get rid of this? Here is where very excellent coordination between the fabricator and metrology team come into play. You need to do something called a negative feedback mechanism. What we do is, in negative feedback mechanism, that form error is primarily compensated by by correcting the tool radius, or by taking the tool path and then measuring the linear scan that happened on the workpiece. You bring that sag table onto the tool path and then adjust it for a zero sum error. That's what we call as tool path compensation to correct the form error. Extract the profile data from the profilometer to generate an error template, which is nothing but a negative. Then error template is whatever you got it, and put a negative feedback with a negative sign. You add that to your tool path. Tool path is modified by point tool positioning comparison. A new compensated tool path once again used. In other words, you are telling the tool to go in a slightly modified pattern so that wherever it caused an error in your previous machining cycle, that error is corrected point by point in the current cycle. So that compensation cycle has to be iterated till the form error is reduced to acceptable tolerance. This is a simple, a typical example where we started with a 3.4 micron error, and after 3 cycles, we landed with 0.18. You can see this. Again, the same thing I'm showing. So here, not only the form errors or the figure error has reduced, but also the roughness also has been reduced. You can see from 0.3, roughness is also there. Only thing, you have to play judiciously your things. So this is the story of metrology and characterization of a precision optical surface that is being used for laser applications. Now, next stage is tolerances. One has to be very much aware of the tolerances. Tolerance is nothing but the error tolerances that has been studied by the designer and has provided to the fabricator. So the job of metrology and characterization team is to see each parameter, whether it is curvature, edge thickness, or center thickness, or the tilt, or the spaces between the components, decenter, conic constant, all these things, the errors in each of these parameters are within the acceptable limits or not. To help the teams, you have parameters called machining parameters, the lap length, the velocity of the spindle speed, and the grit size. We are talking of the tool geometry here, and machining accuracies and other thermal variants. So quality parameters, the outcome parameters are profile inaccuracies, roughness, and these are output parameters. The outcome parameter is image plane intensity. And finally, one has to look at the time that is spent on this as well as the cost. So for best performance, one has to look at the optimistic methodology as well as the pessimistic methodology, and finally go for the midway for tolerancing. So that's what I have to present. Thank you so very much, and any questions I'll be very happy to answer. Okay. So if there are no questions, I thank for the organizers for giving me this opportunity to share some of our work with us, and looking forward to receive any queries. My email is given there, sarepaka.vrg@gmail.com. That can be had from the organizers also. Thank you once again. God bless you all. Have a wonderful time in the conference. Bye.